Hi, my name is Muhammad Akram and Muhammad Kamal. Today I want to present about self-healing concrete means revolutions the built environments. Let's start with the make of a self-healing concrete so exciting. Imagine if our road, bridge and building could actually repair themselves when crackers appear. That's exactly what the material can do. Is the game changers. Because instead of needed construction repair, the concrete take care of themselves. This means less maintenance, few repair, and much longer life for the structure we rely on every day. It's one of the most innovation steps forward in modern construction, helping to make our cities more durable and more sustainable. Next, why do we need to self-healing concrete? So why do we even need concrete that heal itself? We regular concrete crack all the time. It can be from things like temperature change, heavy traffic, or just age. And fixing those breakers is cheaper. In the US alone, we spend over $18 million every year just on repair. And it's not just about money. Cracker and aging concrete can be dangerous. When infrastructure starts to break down, it's put people at risk. Since we use more than 4 billion tons of concrete worldwide each year, finding a stronger, longer-lasting solution has become a big priority. Okay, next, what is self-healing concrete? So how does this amazing concrete actually works? Self-healing concrete is designed to fix small cracks on its own, kind of like how our skin heals a cut. When tiny crack from other to small, they'll even see the concrete crack react and start healing them up without anyone having to do anything. This stops little problem from turning into big one and keeps the structure stronger for much longer. It's smart and nature-inspired solution that could totally change the way we build.
Good evening everyone. Today I like to show you why self-healing concrete is more than a buzzword. It's a practical way to extend the life of our roads, bridges and buildings. On this slide, you can see two pathway a crack can take. First is autogenous healing relies on ordinary cement that never fully reacted during the first cure. When water later seeps into micro cracks, it rehydrates those leftover particles, creating new crystals that seal the gaps. Second is autonomous healing is different. We plan for it from the start. We embed special agent, chemical, mineral or even bacterial that stay dormant until a crack appears. A trigger such as air, moisture or a change in pH wakes them up so they can patch wider, harsh crack and autogenous healing can handle. Okay, for this slide is autogenous self-healing. Let's zoom in. Concrete naturally wants to feed itself but only under the right condition. First, it needs moisture, rain, humidity or groundwater. Second, unreacted cement hydrate again, producing extra calcium silicate gels. Third is over time, calcium carbonate crystal grow and meet together crack that are typically under 0.2 millimeters, about the thickness of a human hair. The downside is a capacity. Older or dry structure don't have enough free cement left to keep healing. Okay, for the next slide is autonomous self-healing or microcapsule technology. Here, the game changer. We embed microscopic capsule about 1/10 the width of a grain of sand filled with liquid healing agent. Step 1, capsule lie dormant for years without affecting strength. Second step is when a crack grows, is like the capsule wall, releasing the agent exactly where it's needed. Step 3, the liquid seeps in by capillary action and polymerase, bonding the crack face like a built-in epoxy injection. Because the trigger is a chemical, the system itself sufficient. No sensor, no maintenance. Okay, thank you for listening.
Hello and hi, my name is Nurfate Bete Hamzani and I will continue my friend of the presentation. Let's begin by exploring polymer and chemical healing agent, a critical component in the advancement of a self-healing concrete technology. Modern self-healing concrete leverage several chemical agents to repair damage autonomously. For example, epoxy-based polymer offer excellent structural bonding and help reinforce the material. Sodium silicate is another key agent, forming calcium silicate hydrate to effectively seal crack. Polymer contribute superior waterproofing essential for durability in a harsh environment, and cyanoacrylate of a superglue compound delivered to rapid healing a small fracture. To make this healing agent effective, we use encapsulation technique be like gelatin microplast for the biological compatibility, glass tube for the control release, and the two custom designed polymer shield that break at specific pressure point to the release the healing agent. Let's look at the measurable impact of this technology. First, in the term of a strength recovery, self-healing concrete can restore up to 85% of its original strength after damage, far outperforming traditional concrete with typical recovery only around 30%. Secondly, studies show a maintenance cost can be reduced by 50% or more thanks for the fewer repair and less requirement of inspection. And finally, one of the most exciting benefits, lifespan extension. With this agent, infrastructure can potentially double its served life, increase from the standard 50 years to the 100 years. These concepts are just not theoretical. They are already being applied in the real-world infrastructure. In the Netherlands, the A76 highway became the first major project to use a bacterial self-healing concrete back in 2015. In London, there are trial sections for the Hungerford Bridge have been monitored since the 2019 for their healing performance. In China, the Jiangyin-Yangtze River Bridge used the technology to the underwater structure component and showing the versatility. And the satellite rail tunnel incorporate it for waterproofing in high stress area. Report from this project show 30 until 40% fewer maintenance intervention in just the first 10 years, proving the value of this investment early on.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nasrul Habib Muhammad Najib and I'm going to presenting about challenges and current. The first thing is technical challenges, and there are 4 points about technical challenges. The first one is ensuring long-term viability of healing agents. Next one is protecting capsules during high shear concrete missing, developing reliable testing and certification standards, and scaling production methods for industrial quantities. Next one is economic barriers. The first one is initial cost premium of 20 to 35% over conventional concrete, difficulty quantifying lifetime economic benefits, and resistance from conservative construction industry. The last one is research frontiers. The point of the research frontiers is multi-stage healing system for repeated damage, integration with structural health monitoring sensors, and optimizing for extreme environments. Okay, the next slide is the last slide, and we're going to talk about the future of self-healing concrete. A sustainable revolution, self-healing concrete is poised to transform construction over the next decade. Projected market growth from 1.4 billion in 2021 to 7.8 billion by 2031. And integration with IoT sensors for real-time monitoring, development of specialized formulations for specific applications, potential carbon footprint reduction through extended infrastructure lifespans. As we can see, as climate change increases infrastructure stress, self-healing materials will become essential components of resilient, sustainable system. And that is all from us. Thank you.